Okay, so up to this point, we have learned how to calculate voltages of voltaic cells. We've learned how to use cell diagrams. We've learned how to calculate delta G and KEQ based off voltage and how those things are all interrelated. We haven't touched the idea of what happens if you're not at standard conditions. We need to deal with that, and it's going to be a little messy, but that's okay. The idea is that the cell potential, which I'm just going to label as an E here, is equal to the standard conditions with sort of a corrective factor. And it works out to 0.0592 volts divided by N, which is the same N it's been in the past couple videos. It's the number of the least common multiple between the number of electrons in the two half reactions, times the log, not natural log, of Q. We have seen Q, but we kind of didn't really do anything with it way back when. Q is something called the reaction quotient. And it's essentially the same thing as Kc or Kp or Keq, but you're not at equilibrium conditions. It's essentially Keq, but not at equilibrium. So it's still products over reactants raised to the coefficients. Okay, so let's try an example. All right, we saw this example in the last video. We had copper becoming copper 2 plus, and then we had, I'm going to leave a space, and then we had silver plus becoming silver solid. And we saw in the last video that this had a standard cell potential of 0.46 volts. Great, everything was fine. But that assumption was that these are solids and these are all 1 molar. Let's see what happens if they're not at 1 molar. What happens if this is only 0.50 molar and this is like 0.30? So similar concentrations, but not 1, like the reduction potential table requires to make any sense. Okay. The first thing we actually have to do is figure out the cell potential of the standard conditions, which we did in the previous video. You just take this side minus that side. It comes out to 0.46. So if everything was 1, this is what it would be. The other thing we need to get this Q value is we need to write the balanced equation. So I'm going to review something that I did a couple videos ago. Reactant, product. Reactant, product. Okay, so what we're going to do is we're going to write those, and then we need to balance everything. Okay, so we have copper solid as a reactant, and we have silver plus as a aqueous as a reactant. And then our products are copper 2 plus silver solid. Okay, if we look at the two half reactions of this, we said that copper to copper solid has 2 electrons, and silver to silver plus only has 1 electron. So this reaction would need to be doubled to make them both 2. So we're just gonna double both of those to make the electrons cancel out, okay, to make our N value come out to 2, which means these are products, these are reactants. Our Q value is going to be, we ignore the solids, is this concentration divided by this concentration squared. So you have to get the balanced equation before you can even do the Q part. Okay, the rest of it's pretty much plug and chug, but this is a little complicated. So the E equals this E at standard conditions, which was positive 0.46, minus this constant, which is 0.0592 volts, divided by N, the least common multiple. This reaction required 2 electrons, this one required 1, so the number of electrons, the least common multiple between those is 2 electrons. Okay, times the log base 10, not log base E, of the reaction quotient, which is products over reactants raised to the coefficients. Well, Cu2 plus is a product, which is 0.5, and then Ag plus is the reactant, and we need to square it. The ones that are solids we can ignore. Obviously, if we had like a platinum electrode and we had two things with concentrations here, we would need to take into consideration both of those. Okay, so looks a little messy, but what you find is that if you plug all this in, let me grab my calculator. Sorry, that might have been a little loud. Okay, I'm going to do the log part first. I'm actually going to do all of this, which is 0.5 divided by 0.3 squared. Okay, going to hit equals, and I'm going to take the log of that. Hit equals times 0.0592 divided by 2. All of this only comes out to 0.022, which means when you take 0.46 minus 0.02, you get a value of 0.44, which means it's pretty close to what we started with. You would have to have a pretty major change in concentration for the voltage to change much. Okay, but this is how you would calculate something at non-standard conditions. Okay, I guess I should circle this equation so it looks important in the notes. Okay, all right, this should be the end of the electrochemistry chapter. All right, thank you guys.